let's pick up where we left off, where we were discussing the transition probabilities from one wave function to another for a given atom. So we said that we would develop through the integration of the function CFI of t, that we would integrate up and find a matrix of transition probabilities. And so that's what we're going to work on now, is how do we get to that matrix of transition probabilities. And all of that is a step along the way towards understanding relative line strengths. So let's share the screen. So working on transition probabilities. So the probability per unit time for spontaneous transition from state I, which is our initial state, to state F into solid angle d omega is given by Wfi d omega, and it's equal to omega Fi, which is the angular frequency associated with the transition from the final to the initial to the final state, times e squared h bar on 2 pi m squared c, m squared c cubed, times a matrix function mfi squared. And that matrix function is the matrix of transition probabilities, where mfi is the integral from 0 to infinity, and the surface integral over the complex conjugate of the final wave functions times an exponential, which is I, k, which is a wave number for this radiation, times r, and I'll explain how those come about in a minute, dot grad the initial wave function of r integrated over a volume. And you might recognize that we can associate this grad with the momentum operator. So that's a momentum operator. Well, sorry, I left out a term, which is epsilon in here, where epsilon is the polarization vector of the EM wave. So it describes the polarization vector of the electric field of the EM wave. Now we've defined in there an omega Fi. Bear with me while I define all these terms. You'll see how they come together in a moment, which is equal to 1 over h bar times the difference in the energy levels, initial minus final. Sorry, that should be final. Now the exponential term that we saw on this last slide, so this term that's here, comes about from making a dipole assumption. So what we do is the exp I k dot r comes from the weak field approximation of the vector potential Vr of t. And you can also expand this into the true dipole form so that exponential of ik dot r is 1 plus ik dot r plus 1/2, just a standard expansion of this term. And the key thing here is that the first one gives a dipole radiation field. The second one is what's needed for quadrupole, electric quadrupole. And the third one is what you might have as a octupole. Now, standard transition, permitted transitions in atoms can be approximated as a simple dipole transition. If we consider things like LS coupling, where we need to consider then the magnetic moment of the transition, then we may have to bring in the quadrupole or the octupole terms, but these are much, much weaker than the dipole term for irradiation. So we treat our first pass at treating spectral radiation is to treat the radiation field as a dipole field. And that makes things a lot easier. It's also worth pointing out that the omega Fi is equal to the inverse form of this transition. And that's not surprising if we move from one energy level up to the top energy level. That frequency of that transition is going to be the same as if we move from that top level down to the bottom level. So that's a fairly obvious thing, but it's important to know. So it can be shown that every student's favorite word, but I don't want to go through the full derivation. It can be shown that that this matrix function MFI is quite simply the mass of the electron over h bar times the frequency of the transition from the final to the initial through the Fi transition times the polarization vector times dotted with a term we call RFI. And this is not just the R of the wave function. This is a slightly more complicated term. Where that R comes from, RFI, is that it absorbs a lot of what was inside that integral with the wave functions for the final state and the wave function of the initial state with the R vector in between. This term here is related to the dipole moment. So the dipole moment of the system is simply the electron's charge times this R. So all of that comes about through assuming that we have a dipole transition. So we make the dipole approximation and expanding out the exponential, and allows us to set in place the dipole moment there. So we'll stop at that point and start the next lecture developing a little bit further into where we can go with that.